Question 1, let's work out this, and then we'll just summarize the last part of the notes and have a look through those. So 41 degrees then, 36 minutes, 12 seconds, plus 19 degrees, 40 minutes, 21 seconds, equals 61, 16, 33. 61 degrees, 16 minutes and 33 seconds. Next one, 183 degrees, 46 minutes, 37 seconds, minus 91 degrees, 56 minutes, 21 seconds, 91, 50, 16, 91, 50, 16 seconds, 50 minutes. Okay, last one then, 209 degrees, 37 minutes, 24 seconds, plus 47 degrees, 18 minutes, 41 seconds, minus, on the last part, is 153 degrees, 52 minutes, 39 seconds. 103, 326. 103, 326. Okay, so that's that one done. Let's have a look at the notes continued then. Now, sine has multiple solutions, but you can get one from the calculator. We're in degrees mode. If we do shift sine then of 0.7, to undo sine you do shift sine and 0.7 on the calculator. That's how you undo a sine. 44.4 degrees. We're in degrees mode. So shift cos of 0.25. So shift cos then of 0.25. You get 75.5. And then shift tan is here. Undo the tan, shift tan of 0.38. And it's 20.81, 20.8 degrees. Shift tan of 0.38, yeah, is 21. And the notes has got 61 degrees, which it isn't, because tan 61, if you look at it, if we do tan of 61, you won't get, you'll get somewhat bigger than 1. Yeah, okay, so that's that. Good. Right, let's have a look at this then. The angles in a triangle add up to 180 degrees, and we've got SOHCAHTOA in right-angled triangles. This is the sine, this is the cosine, and this is the tangent ratio. The sine is opposite over adjacent, O over H. Cosine is A over H. So sine is equal to O over H. Cosine, this is how you read the formula, is equal to A over H. And tan is equal to O over A. Opposite over adjacent. So this is the formula. It's 3 formulas in one, and we need 2 of any 3. Okay, so we need 2 of any 3. So I hope that's clear. And it's probably best explained in examples anyway. So here, for example, let's tick off we got as far as the angle 50 is concerned. We haven't got the opposite, we haven't got the adjacent, we've got the hypotenuse. So we've got the sine, cos and tan of the angle, because we can work that out. We've got the hypotenuse. So if we use this one, 2 of any 3 we've got, we can find out the opposite, can't we? Why? And if we use this one, we've ticked off 2 of those 3, haven't we? And we can find out the adjacent. Don't forget, if we find out the opposite from here, we've actually also got that one out subsequently, and we could then use that one to get the adjacent. So it's our choice. So I'm just going to work it out over here then. Scratch this and just have a bit of workspace here. So we said sine was okay to use. Sine 50 then is equal to the opposite over the hypotenuse, isn't it? The y over 10. So that tells us what y is. Move the 10 up to times 10 sine 50. And we can tap that in the calculator. 10 times the sine of 50 degrees, and we're in degrees mode, so that's fine. 7.66 units. Now we've got y. We can put it in the diagram, and we can tick off the opposite now. And then we can use either of these two now. This one comes into play now, or this one, to get x. Let's use cosine, because we had it already, so why not? Cos 50 then is adjacent over hypotenuse x over 10. So that tells us what x is. Move the 10 up to times. 10 cosine 50. Let's go back to our calculator. And let's put cos in. 10 cos 50. 6.43 units. And we can put that in the diagram as well. Okay, so that's that one done. Move on to the next one. Okay, good. So here, what have we got then? We've got this angle. So we can write SOHCAHTOA and see what we've got. We've got the angle, so we've got the sine, cos and tan of it from the calculator. We've got the adjacent, haven't we? And that's what we've got. So we can use 2 of any 3 here and 2 of any 3 there. So let's use the cosine then. And that way we'll get the x, won't we? So cosine of 35 is equal to the adjacent over the hypotenuse x. So we can move the x up, and at the same time I'm going to move the cosine down. 4 over cos 35 degrees. So 4 divided by cos 35 degrees, 4.88 to 2dp. So that would be 4.88. And now we've got the adjacent, the hypotenuse, haven't we? So we could tick that one off. So this one could come into play now if we wanted. But let's use the tan. So tan of 35 then is equal to the opposite over the adjacent y over 4. So opposite is y. Yeah, that's right. Y equals 4 tan 35 then. 4 times tan 35. 2.80 to 2dp, I think. 2.80, yeah, that's fine. So we could put that in the diagram here, 2.80. Last one then, let's have a look at this. Let's just get rid of this stuff. Okay. So let's write SOHCAHTOA out then. We need 2 of any 3, don't we? So what have we got? We've got the angle 57, so we've got the sine, cos and tan of it. We've got its adjacent, so tick off the A. And that's it, that's all we got. We need 2 of any 3. This one will give the hypotenuse. And this one, straight away, will give the opposite, won't it? So here, cosine of 57 is equal to the adjacent over x. So that tells us what x is, doesn't it? Move the x up, and then move the cos 57 down. 8 over cos 57 degrees. 14.68, 14.69. There's that one. And the tan, as we said before, the tan of 57 then is equal to opposite y over adjacent O over A. Y over 8. So y is equal to, move the 8 up, 8 tan 57 degrees. So 8 times tan 57. 12.32 units is the value of y. 32 and x was 14.69 to 2dp. So that's that part done then, and that's how we use SOHCAHTOA, and we need 2 of any 3. Now we've got Pythag, haven't we? So we need the formula for Pythag. Here's the diagram to get Pythag. It's the longest side squared is equal to the other 2 sides squared and added. That's Pythagoras' theorem. and we get it from this. So we could have a quick look at it just to verify. Don't know if you've seen the proof before, or a proof of it before. Let's have a quick look at it for a minute or so. I've just drawn a triangle here, just a general right angled triangle. This is a right angle. Labeled it ABC and labeled this theta. And then if that angle's theta, and this is not, I've dropped a perpendicular here at the point D I've labeled. From here, I've dropped a perpendicular here. So if this is an angle, this is 90, this is 90 minus theta. So because this is 90, this must be theta as well, mustn't it? So sine theta then, if we look at the sides, if this length is x, which we don't know what it is, and the whole distance is c, then this is c minus x. So sine theta is, now sine theta, let me just remind myself. Okay, sine theta, we can get it from two places here. C minus x opposite over hypotenuse. And we can also get it from here. And on this right angle triangle, it'd be opposite over hypotenuse b over c. So that tells us then, this is a bracket because there's more than one term. Move the c up, c minus x, and move the b up to be with the other b to make b squared. This is c squared minus cx equals b squared. So cx then is equal to c squared minus b squared, isn't it? So that's the first piece of information. Now I'm going to do the same thing, and I'm going to look at cos theta now and see what that gives us. So that's the first thing to notice. Now cosine theta, what do we get from that? Adjacent over hypotenuse, so that's a over c, and that's equal to cos theta here is adjacent, which is cos theta. Well, we can get it from here as well, because this is a right angle, can't we? It's hard to get it from here because we don't know this side easily, but we know it from here. Cos theta will be adjacent x over a. So move the a up, a squared is equal to x times c. See, replace that with that. So I'll put it in here. C squared minus b squared is equal to, replace the x, the other cx with a squared. And that tells us then that c squared, a squared plus b squared equals c squared is what that leads to, which is Pythag. So that's Pythagoras' theorem then. So now we can use it in these examples that follow. So here, the longest side squared is equal to the sum of the other two sides squared. 4 squared plus 3 squared. 16 and 9 is 25. Square root both sides, x is 25. Here, 13 squared is 169, is equal to the other two sides squared, the x squared plus the 5 squared, which is 25. So x squared equals 169 minus 25. Square root both sides, we get 12. It's a positive square root because these are lengths of sides. Here, we've got x squared plus 1 squared equals 2 squared, don't we? So x squared is equal to, this is 1, this is 4. 4 minus 1 is 3. So x is equal to root 3. So this is a 1, 2, root 3 triangle. And these are 3, 4, 5. And this is 5, 12, and 13 triangles. Well-known right-angled triangles. We can get standard trig, some well-known trig ratios from equilateral triangle and a 45-degree triangle. Take it as 2, 2, 2. 60, 60, 60 equilateral triangle, side length 2. 2 cos 60 is actually, if you tap it, you'll get, well, this would be 1 here and 1 here, wouldn't it? And this, if that's 2 and that's 1, this has to be root 3 by Pythag, because this squared and this squared must add up to 4, because 2 squared is 4. So that's root 3. So straight away we can see that sine 60, see here, is root 3 over opposite over hypotenuse, root 3 over 2. You get them all from this cos 60, adjacent over hypotenuse to half. Then this angle here is 30,